And we're going to go over a couple of more problems. Isaiah can see what I'm showing you, but you all can't see anything, can you? We're going to go over a couple of problems that will kind of maybe practicing this again, how to find the tangent at a particular line and so forth. One of the things that I want to tell you before I forget would be that your quiz tomorrow in class is going to cover, it's going to cover derivatives through today. It's going to cover the product and the quotient as well. All right. So I want you to make sure that you go home and you practice the product and the quotient. We've had a lot of practice right now on the polynomials, right? Okay. That's what we've been doing. Taking the limits, right? Finding the derivative based on a limit. And all we're doing today, I say that, but we're focusing on product and quotient today. So we will have plenty of opportunity, I think, to practice the product and the quotient rule before we leave. So that's going to be on the quiz tomorrow. Okay, I'm just telling you that right now. Okay, so having said that, and I wanted to make sure that y'all could practice those problems right there. We were talking, and I'm going to just really mention this very briefly because maybe I'll come back and talk about it on Friday. That problem we were looking at here, I had to go back and remember what magnitude was, right? Magnitude and velocity and speed. So technically, speed is just the absolute value of velocity, okay? So the question that we were looking at here says, at what time does that instantaneous velocity have its greatest magnitude? What time does it have its greatest speed, in other words, right? And if this black line right here represents the derivative of the function that we were originally looking at, then you're just looking for at what point, because this line is the velocity with respect to time, isn't it? It's its speed with respect to time. So if you're looking at that, you can come down to the bottom and you can see that the speed of the whatever it was is the greatest at 10 seconds. And so the speed was 60 miles per hour, I think is what we were looking at. So that's what that question was asking, and I didn't answer it to you yesterday, but that's how we're looking at that, okay? While we're here, what do you notice about where at what point is the, what is this, a rocket? Did y'all hear the rockets this morning going off? Or the engines? What is happening here? At what point is the rocket either increasing anymore or decreasing? At 4, right? It reaches its peak. And what we were talking about yesterday, Isaiah has pointed this out to us, right? It happens at those maxes and the mins. Everywhere you have that point in which you're making a curve, right? Where you reach your maximum point or you reach your minimum point, relative max and mins. Notice what's happening here on the derivative. That's an x-intercept. That's what I'm wanting y'all to kind of make the connection for, right? So on this portion of the rocket's trajectory, right, it is increasing. The derivative itself is just positive, right? The function is increasing, the derivative is positive. When the function is neither increasing or decreasing, the derivative has an intercept, right? The derivative is 0 because the slope of the line is 0, right? And here we have the function itself is decreasing and the derivative is negative, okay? So when the function is increasing, the derivative is positive. When the function is decreasing, the derivative is negative. And when the function is neither increasing or decreasing, right, it's at its max or min, then the derivative is 0. The derivative has an x-intercept, okay? All right, and that's how those kind of line up right there. We're going to keep practicing that, all right? We're going to keep looking at that as we move on. All right, so what we're going to talk about today is this product and quotient rule. The product and the quotient rule. So we have learned what we talked about yesterday was the constant multiple, right? Or the constant. We learned the the power rule. We know the constant multiple rule, the sum and difference rule, right? Those are the ones that we've done so far, as well as the derivative of E. What's the derivative of E? Right, the derivative of E to the X is E to the X, right? Okay, so what we're gonna do now is we're gonna talk specifically about the product rule, but we wanna add in, oh, by the way, we also wanna discuss, we're gonna hit on the derivatives of the trig functions, okay? So again, this is just memorization. These are just memorizations. The derivative of sine is cosine. The derivative of, that should be the derivative of cosine. Let me change that. The derivative of cosine is negative sine. So the derivative of sine is cosine, the derivative of cosine is negative sine. Tangent would be secant squared. There's that Pythagorean identity. Remember, those were related using the Pythagorean identity, tangent and secant. And therefore, when you look at secant, notice that the derivative of secant is secant x tan x. Maybe that'll help you remember those. And then you have that same kind of concept if you're thinking about cotangent. The derivative of cotangent would be negative cosecant squared. And cosecant is negative cosecant cotangent. Okay? So once you have those copied down, we're going to talk about the product rule. I'll give you just a second to make sure that you have those copied down. Because the product rule and the quotient rule are just kind of special ways for us to look at, or they're just special formulas, I would say, in essence, for us to be able to take the derivative. So when we look at the product rule here, it says if f and g are both differentiable functions on x, then their product can be found. The product of f of x, g of x can be found, and the derivative is given here. The derivative of the first function f times the second function g plus the first function times the derivative of the second. That's what that says. Now, let's look at this first example here, x times 9 plus x. That's the first function we want to take the derivative of. Now, we know that the easier method here in this particular case would actually be to distribute that x, get rid of the parentheses, and take the derivative using the sum and difference. That would be way, way easier than using the product rule here, but we're going to practice the product rule on something that's easy first, okay? So if we're talking about, notice that we have in our explanation of this product rule, we're going to need to know the function as well as its derivative for both f and g in order to apply this property. So if I were looking at this, I would say, okay, I have I have f of x, which is going to be equal to x. And I'm going to let g of x be equal to 9 plus 2x. So the derivative then of f of x is equal to 1. The derivative of g would be equal to 2. Okay? So far, that's the same thing we were doing the other day. So when I put this together and I find the derivative of h, that says that we're going to take the derivative of the first function, 1, times the second function, 9 plus 2x, and add that to the first function, f of x, times the derivative of the second function, 2. So we end up with 1 times 9 plus 2x, or 9 plus 2x plus 2x, which is equal to just 9 plus 4x. And I feel like we worked that problem yesterday or on your notes or something. It looked awfully familiar to me, but anyway, that's how you do it using the product method. Now, if I had come up here, like I said, and maybe we had written h of x instead as 9x plus 2x squared and took the derivative using the sum product that we did yesterday, you can see that the derivative is still 9 plus 4x. Okay? But sometimes that doesn't always work for us. All right? Sometimes that is not always going to work for us. Let's come down here. I want to look at this next problem. I don't want to do that one that was up there. I'm going to look down here at C. So if we apply this same concept, I'm going to let f of x be that first parentheses, 3 minus 2x squared. Therefore, f prime has to be negative 4x, correct? Yeah? Keep you straight here. All right. So g has to be 5 plus 4x. G prime has to then be 4. Okay, so h prime is going to be negative 4x, the derivative of the first times the second function, plus the first times the derivative of the second. 3 minus 2x squared times 4. And now we're going to simplify. I would have negative 20x plus 16x squared plus 12 minus 8x squared, or 8x squared, huh?
It'd be a negative.
Which part?
The 16x squared would be negative.
Oh, you're right, thank you. So it would be what, negative 24? Negative 24x squared minus 20x plus 12.
The 2x squared times the 4x, once you actually distribute it out. X to the power,
But then I take the derivative and I would get something less.
which would bump it down to the square.
Yes. Okay. All right. Well, let's look at the next one then. So here we're going to take the derivative of x e to the x. So if we let f of x be equal to x, f prime has to be equal to 1. G of x is e to the x, but g prime of x, again, is equal to e to the x. So the derivative of y becomes f prime times g plus x or f times g prime e to the x. So in other words, we would have e to the x plus x e to the x. You could also write that e to the x times 1 plus x. Okay. All right. Let's try our hand at this next one. I've got y is equal to cosine x minus 2 sine x. Okay. So this is really almost not a product rule, is it? What's the derivative of cosine x? Negative sine x. Minus 2 times, what's the cosine of sine x? It's just cosine, right?
Yes.
Oh. Yes. So negative sine x minus 2 cosine x. Right? Just kind of applying some of those properties that we were using above.
So you wouldn't worry about like, wait, never mind.
All right, let's look at another one down here. Find the equation of the line tangent to the graph of the given function at the indicated point. So similar to what we were looking at before. Okay. So if we want to apply the product rule here, I'm going to let and I'll just call it f is going to be equal to x to the 4th plus 1. F prime would have to be 4x cubed. If I let that be f, the first binomial. The second binomial, let's let that be g. So I would have x squared plus x. G prime would have to be what? 2x plus 1. Okay. So the derivative of the function is going to be 4x cubed times x squared plus x plus x to the 4th plus 1 times 2x plus 1. And now we need to simplify that. Four x to the 5th plus 4x to the 4th and then multiply that binomial out. We'll see if we can all get the same answer. Okay, could you all get 6x to the 5th plus 5x to the fourth plus 2x plus 1. Okay, find the equation of the line tangent to the graph if this is the function at the indicated point, similar to what we were doing when you started class today. So the first step in this case, I suppose, would be to find the derivative, right? So that was our first step, is find the derivative. Now that we know what the derivative is, let's find the slope at x is equal to 1. Right? The slope when x is equal to 1. So the slope is going to be equal to the derivative evaluated at 1. So 6 times 1 to the 5th plus 5 times 1 to the 4th, 2 times 1 plus 1. So we get 14 when we evaluate the derivative at 1. In order to use the point slope formula, I have to have a point. And at this point, at this section of the game, I don't have a point yet. So the third thing I'm going to do is I'm going to find the point on the curve, which is the original function. So f of 1 would be 1 to the 4th plus 1 times 1 squared plus 1. One plus 1 is 2, times 2 would be 4, right? Okay. So I now know that the point on this curve is occurring at 1, 4. And then we can find the point slope formula. Or we can use the point slope formula. Y minus Y1 is equal to M times X minus X1. Or Y is equal to 14X minus 10. Okay. So those are the kind of the steps that you were following when you were trying to find it on that practice problems, right? Okay. Okay, that's when we want to know the equation that's passing through that point, right? The derivative gives us the formula, if you will, for any slope, for the slope of any line on the original function. That's what the derivative tells us, okay? Okay. What if, now we're going to talk about the quotient rule. So we talked about the product rule, now we're going to look at the quotient rule. And when you're doing the quotient rule, we're going to do something similar that we did before. In other words, it's helpful to kind of break out the functions and their derivatives of both f and g. In other words, if we let f be the numerator and g be the denominator, it's kind of helpful to identify the numerator as well as its derivative, along with the denominator and its derivative. And the way that we put them back together is low, I'm just going to write this on here, you're going to write it on your paper. D high minus high, D low, all over low squared. All right? That's how we're going to put it all together. What that means is I'm taking the denominator, which is low, multiplying it times the derivative of the numerator, minus the numerator, which is high, right? times the derivative of the denominator all over the denominator squared. Low D high minus I D low over low squared. Or you can just remember the F prime G minus F G prime over G squared. Whatever's more fun for you, okay? Let's look at this problem right here. Applying the quotient rule specifically to this problem. So if I know that the numerator is represented by 4 and the derivative of that would be 0, the denominator is represented by x to the 6th and its derivative would be 6x to the 5th. So low would be x to the 6th times the derivative of the numerator, which would be 0, minus the numerator times the derivative of the denominator, all over the denominator squared. So I would have negative 24 x to the 5th all over x to the what? 6 times 2 would be 12 in the denominator. Simplify that, y prime becomes negative 24 over, because rules of exponents say I'm going to subtract those exponents, right? When we have a quotient. So I would have x to the 7th in the denominator. Is there an easier way to work this problem? Absolutely. What was that? Right. So just like we saw in that first problem where I could have just used kind of some algebra to simplify it and then use the sum or the difference to be able to simplify it, and we could have done the same thing here and come up with the same process, right? Okay. But that doesn't always work. So we have this other example over here, 4x plus 8 over 6x minus 1. So if I let the numerator be 4x plus 8, the derivative of the numerator would be 4, right? Denominator is 6x minus 1, and its derivative would just be 6. So putting this back together, we would have low d high, 6x minus 1 times 4, minus high, 4x plus 8, d low over 6, or times 6, all over 6x minus 1 squared. Now let's simplify. Y prime is going to be 24x minus 4 minus 24x minus 48. Leave the denominator factored. 6x minus 1 squared. So the numerator just becomes negative 52 over 6x minus 1 squared. A lot of times when you're simplifying these these rationals like this, if you'll leave the denominator factored in its factored form, you might be able to clean up the numerator and then cancel common factors. Okay, so don't expand it yet. I mean, I wouldn't even expand it at this point. We don't get anything new out of it, do we? Okay. All right. Let's try You getting the hang of this? Yeah, fairly straightforward. Okay, well, let's do D together then. So the numerator, which would be 4x to the positive 1/2, right? Its derivative would be 2x to the negative 1/2. The denominator is going to be x squared minus 2. Its derivative would be 2x. So the derivative looks like low, which is x squared minus 2 times the derivative of the high, which is 2x to the negative 1/2, minus 4x to the 1/2 times 2x. Okay, now all over the denominator, x squared minus 2 squared. So we're going to simplify this. I'm going to take the 2x to the negative 1/2 and distribute it in, and I would get 2x to the positive 3/2, right? Minus 4x to the negative 1/2. Minus 8x to the 3/2. All over the denominator. X squared minus 2 squared. So far, so good?
Wait, why do you do 3x? Positive 3x?
1/2 times 1, or actually,
No, I meant the x squared minus 2 times 2x. Negative 1/2.
so if the bases are the same, which they are, they're both x's, I'm going to add their exponents, right? I'm going to add this exponent with this exponent, right? 2 minus 1/2, 2 minus 1/2. It's 3/2, right? 2 minus 1/2 is 3/2.
Yeah. I just didn't.
Y'all are making me think I don't know how to do that one by myself.
I didn't
Come
know.
on now.
That's why I asked.
All right. And then the next one would be 1/2 plus 1, right? Which would be 3/2 as well. Okay. Phew. Okay. So now we have negative 6x to the 3/2 minus 4x to the negative 1/2 all over the denominator. And we're going to call it good. That's good. That right there. We cleaned up the numerator a little bit. We have the denominator down there. Combined our like terms. Okay, change it to a rational. I don't really need to change this back. I don't really feel like I need to. Check your homework to make sure if they want you to not leave your answers as negative exponents or not leave your answers probably as the other option would be to not leave your exponents as rationals. Then that's when you know to change it back to a radical form, right? So that first term would look like negative 6 times. What would that first term look like? Negative 6 times what? Square root of x cubed, right? Okay. All right, just making sure that we all remember how to change those back and forth. Okay. Quotient rule. Now let's try that here. Find the equation of the line, tangent to the graph of the given function at the point. If we know x is equal to -1 and the function is 3x over x plus 4. So we're gonna find the derivative. The derivative f is 3x, so f prime has to be 3. G is x plus 4, so g prime has to be 1. So the derivative is x plus 4 times 3 minus 3x times 1 all over x plus 4 squared. Or 3x plus 12 minus 3x over x plus 4 squared. Or 12 over x plus 4 squared. Okay, because the 3x is canceled. So we found the derivative. Let's find the slope. The slope at x is equal to -1. So f prime of -1 would be -1 plus 4 squared. So 3 squared, so that'd be 12/9 or 4/3. So that's the slope at that point. And now let's go make sure we have an actual coordinate. So the point on the curve, f of x, is f at -1. Which would be -1. So the point is -1, -1. X is -1 and y is -1. So the equation is going to be y minus a -1 is equal to 4/3 times x minus a -1. Y plus 1 would be 4/3 times x plus 1. Distribute your 4/3 and then subtract 1. And you get y is equal to 4/3 x plus 1/3. Okay? You getting the hang of that one now, right? Kind of multi-step, but it's kind of straightforward, I think, if that's what you're looking at. Okay. Let's practice a couple of these functions here. Since we just learned the trig functions, refer back to them, all right? Till you get the hang of them. No sine and cosine, those are the ones we use a lot. But then start memorizing the rest of them, okay? So the derivative of sine is cosine, the derivative of cosine is negative sine. Those are the two we use most. All right, so if I wanted to know what the derivative is of 3 secant x minus 10 cotangent x, This is a straightforward sum derivative or difference derivative, right? I don't have any multiplication or division going on. So G prime is going to be 3 times the derivative of secant was secant tan x minus 10 times cotangent, which is negative cosecant squared x. And then simplify. Which just changes that to 3 secant x tan x plus 10 cosecant squared x. All right. Now let's look at the next one. We good with that one? All right, let's look at this next one. So here, we have a lot going on, don't we? We have this first function. We're going to take the derivative of the first function. And then we're also going to take the derivative of the second function. Notice what's happening in the second function. We have a product between w squared and tan w, don't we? Okay. So if we wanted to think of this, we know that in the second function over here, f is w squared, then f prime would be 2w, wouldn't it? If g is tan w, then g prime is secant squared w. Positive. Okay. So the derivative of h, for the first term, we just use the power rule, which would be 3 times negative 4w to the negative 5 minus, and then here we have the derivative of f 2w times tan w plus f, which is w squared times the derivative of g, which would be secant squared w. So we would end up with negative 12 w to the negative 5th minus 2w tan w plus w squared, or minus, excuse me, w squared secant squared w.
Wait, isn't it all supposed to go over tan w squared? Because they're supposed
It's
to.
product.
No,
It's product. So it's just the first times the derivative of the second plus the derivative of the first times the second. Okay. All right, let's finish this off doing the last one over here since it's a quotient. Okay, so we have sine t over 3 minus cosine t. So if the numerator is sine, what's the derivative of sine? Okay. So g, or the denominator, is 3 minus 2 cosine t. And its derivative would be negative 2 times negative sine t, or in other words, 2 sine t. Right, so the derivative of t, of p, is the low number 3 minus 2 cosine t times the derivative of the high, which is cosine t, minus the high, which is sine t times the derivative of the low, 2 sine t, all over the low, 3 minus 2 cosine t squared. So then we're going to simplify. The cosine t minus 2 cosine squared t minus 2 sine squared t all over the denominator. Now, we're going to clean up this numerator. I've got 3 cosine t. I am going to take out of this section here, I'm going to factor out a -2. Minus 2 times cosine squared t plus sine squared t. Jonathan, what's that? All over 3 minus 2 cosine t squared. So this is 1. Cosine squared plus sine squared is 1. Yep. So I get 3 cosine t minus 2 over 3 minus 2 cosine t squared. That's the derivative. It's not, it's,
So why this converted?
It's easy to get mixed up.
it is,
Yeah,
it's
that's
easy to
what-
make a mistake, right? It's easy to make a mistake at least, okay?